Hi, welcome to StatStuff. I'm Matt Hansen. In this lesson, I'll introduce you to some descriptive statistics that aren't very commonly used. However, these statistics can be very helpful when trying to quickly analyze data. It would help if you had previously viewed some of the lessons from the measure phase that went into more detail about distributions, central tendency, and spread. But for now, I'll begin by defining what are descriptive statistics.
Descriptive statistics are referring to a variety of standard statistical metrics that are used for analyzing data. Some of the most common ones would include the mean, standard deviation, the median, the mode, and certain things like that we've gone over in many other videos in the past. Now, Minitab can also show you some more detailed descriptive statistics along with a graphical summary. The graphical summary I'm about to show you is the example that's used in other examples based off of a data file that's available on our website, and it's based off of metric A as part of that data file. So if you go to Stat, Basic Statistics, and Graphical Summary, this is the kind of output that you would get when you are doing it on, in this example, metric A. It gives you the distribution plus a blocks plot plus the confidence intervals, and it gives you some extra details off to the right hand side. Now, that's not the only place where you can get some descriptive statistics. You can also go into Stat Basic Statistics and Display Descriptive Statistics, and you get this particular dialog box that has a list of all these different statistical items that you can choose from to view. By clicking OK, you'll get this kind of output that comes from Minitab. So you've got the example that shows over here where you have some of the most critical ones or the ones most commonly used during the graphical summary, or you can get a full list of more descriptive statistics when you get this kind of output from Minitab. And what we're going to go through next is going to show some of these critical items that aren't as common as some of the ones you might see in a graphical summary, but there also can be some very helpful ones in here that we'll explore now in this video.
Now let's look at two basic types of descriptive statistics.
Now, we can categorize descriptive statistics in a couple of ways, and it really depends on what it is that they're trying to measure and how we would categorize it. So it's either going to be based off of whether they're measuring central tendency or whether they're going to be measuring variation or spread. So we're going to go over next is a chart that describes all those different items. First of all, some of the more common statistics that we'll look at when it's measuring central tendency would include the mean, which is also the average, or the median, which is the 50th percentile, or the mode. Now, for some of the less common statistics that we would use for measuring central tendency would include the standard error of the mean, or SE mean, or the trimmed mean, or the mean of the squared successive differences, or MSSD. We're going to go over these in more detail in this lesson. And some of the most common types of statistics we would use for measuring variation or spread would include like the range, like the min and max, deviation, variance, standard deviation, stability factor, or even the interquartile range, which is IQR. But some of the less common ones that measure variation or spread that we're going to look at in this lesson would include the coefficient of variance, COV, and also skewness and kurtosis.
Okay, first let's begin by looking at those less common statistics that are used for describing central tendency.
Well, the first statistic that we're going to look at for measuring central tendency is going to be the standard error of mean, or SE mean. And what we want to show is several things the characteristics behind it. First of all, the way it's calculated is by taking the standard deviation dividing by the square root of the number of items that are being evaluated in the sample. Now, the purpose behind using this particular metric is to determine the confidence interval of the mean. The way we interpret it is that we would look for a smaller SE mean. That is, the smaller it is, the better it is, indicating that we have more confidence that we have around where the mean is for the population. So from a practical standpoint and how we apply this, you would take the SE mean and we multiply it by the number of standard deviations for which you want your confidence interval. So as an example, if you want 95% confidence around the mean, then what you would do is you would use 2 standard deviations. Obviously, if you'd want 99% confidence interval, then we'd use 3 standard deviations. But for this example, we'll assume we want a 95% confidence interval around the mean. So we would take the mean and we subtract from that the SE mean times 2 representing the number of standard deviations. That would be our lower end of the confidence interval. And then on the upper side, we would take the mean and we'd add to that whatever the SE mean is times 2. And that would give her the upper portion of the confidence interval. Between these two values, that would give us the total interval of where our mean should fall for the entire population. So the result tells us that for every data sample that you take from the sample population, or from that same population, there's a 95% chance that your mean's going to fall within that range, and there's within that confidence interval. Now, the smaller the interval, then the more confident you can be about your mean, the more precise it is. Now, how is it that you can make your SE mean smaller, and that is making it better? Well, you can do it two ways, either by decreasing your standard deviation as shown in the calculation here, or you can increase your overall sample size. In either case, it's going to make your SE mean smaller, which would make your confidence interval smaller and more precise about understanding where your mean would fall in the total population. Well, another statistic that we want to look at is the trimmed mean. So for characteristic-wise, we would say that it's calculated basically by looking at the 5th percentile and 95th percentile and trimming those away from your data set. So it's taking away what is from up to the 5th percentile and trimming away what's above the 95th percentile within your data set. And by the purpose of doing that is to recalculate the mean without considering those outliers that might fall within the lower 5% and upper 5% of your data set. Now, it's interpreted by saying if the trimmed mean is very different from your overall mean, then there could be some severe outliers that are influencing the mean. So what we'd use as a practical application is we would take the trimmed mean as a quick check to see how significant the outliers are that could be influencing the overall mean. If we see that the mean shifts a lot, then examine the outliers to see if they should be removed from the analysis as possible anomalies. Now, if the mean doesn't shift much, then the outliers in the data should probably not be removed from the overall analysis. The last one we're going to look at for measuring central tendency is going to be the mean of the squared successive differences, or MSSD. The way it's calculated looks a bit complex here, so let's go over the purpose of it. It actually looks more intimidating than what it really is, but the purpose behind it is that it's used to validate the randomness of the sample data set. The closer that this MSSD calculation is to the variance, then the more likely that the sample data is truly random. Now, variance is calculated by taking a deviation of each data point to the sample mean. That is, how distant each one of those are from the sample mean. However, the MSSD is a little bit different. It's calculated by the deviation of one data point to another successively through the data set. So instead of taking each data point as a deviation from the mean, it's going to 0.1 and comparing that to 0.2. And then comparing 0.2 to 0.3, and then 0.3 to 0.4, and so on, again in successive order. If the sequence of the selected data is truly random, then they should arrive at around the same value, at least really close to the variance value. Now, again, since this formula looks a little intimidating, all you have to do in order to practically apply this is just compare whatever the MSSD results are with the variance in the descriptive statistics results. If they're relatively close to each other, that is, if they're within the range of about 90 to 95% of one or the other, then your data set sequence is probably going to be random. If there's a big difference, a big gap where one is less than 90% of the other, and again, it doesn't matter which one is greater, which one's less. If there is at least more of a gap like that where one is less than 90% of the other one, then chances are your data may not be random. Now, obviously, you can use other tools to assess that randomness, but this is just an additional one that can be used to help assess, again, the randomness within your data.
Now let's begin to look at those less common statistics used to describe variation or spread.
Well, the first statistic that we're going to look at is the coefficient of variance, or COV. The way that's calculated is by taking the standard deviation divided by the mean, and we multiply that by 100. The reason we use this is that it normalizes the variability for a particular measurement. So how we interpret it is we take this smaller COV, we would say that that's better. That is, where it's closer to 0, then that's better, meaning that there's not a lot of variation as significant relative to the mean. Now, from a practical standpoint and how we apply this kind of thing is we use this when we want to compare the variation between two different types of metrics. So let's say we're trying to compare a couple of different metrics that we might see at a call center. They might have call duration as one particular metric. Let's say the average for that is about 600 seconds, which is about 10 minutes, and a standard deviation of about 100 seconds. We might have another metric of customer satisfaction, or CSAT. We might say the metric there is around 85% for the average, but the standard deviation is about 15%. Well, if you notice, there are completely different types of metrics. One's a continuous value using seconds, and the other one is more of a discrete value reflected as a percentage. So how do you compare between these two when they have different sets of variation? Well, in comparing the two, if we were to guess at the variation, having 100 seconds seems pretty significant, so it looks like we might have a whole lot more variation for call duration as a metric. However, when we apply the COV, we would see actually for call duration, its COV is 16.7, and the COV for CSAT is 17 16.6. Since 16.7 is smaller, then we would say that the call duration actually has less variation relative to its mean compared to CSAT. So again, it's a way of just comparing completely different metrics to each other, even when they have different bases on them. At least when you have these measurements of mean and standard deviation, you can do that kind of comparison. The next statistic that we're going to look at is skewness. So the purpose behind that, it's a way for identifying how skewed or how biased our data is. So the way we interpret is using a scale like this. If the skewness value is going to be less than 0, we would say that's negatively skewed. That is where the outlier data points are closer to the y-axis. If we see that the skewness value is around 0, then it's relatively unbiased. That is, there's little or no skewness or bias in the data at all. If it's greater than 0, then we would say it's positively skewed. That is, the outlier data points are further away from the y-axis. So using the examples that we're looking over here on the left-hand side, we would see this green distribution that's represented here is actually more of a positively skewed because the outlier data points are further away off to the right-hand side, further away from the y-axis, compared to this blue one, which is more of a normal type of distribution, which is probably going to have a skewness of about 0 or something very close to 0. Compare that to the red distribution that's on here, where most of the outlier data points are closer to the y-axis. Well, then we would say that's more of a negatively skewed type of distribution. So from a practical standpoint, we could even have skewness in normal distributions. And just because the value that we might be measuring has skewness doesn't mean that it's non-normal or that it has like an overabundance of bias within the data and we can't treat it as normal. It only tells you where more of the outliers are, where they're residing, that it's closer or further away from the y-axis. The last statistic that we're going to look at from a variation standpoint is going to be kurtosis. The purpose behind this is it's a way of measuring the shape of your normal curve where your central tendency is. Now, we would use a similar scale as we saw for skewness. In this case, when the kurtosis is less than 0, we would call that a platykurtic. That is where the bell curve is flatter than usual. If it's around 0 for kurtosis, then we would say there's no kurtosis at all. It's relatively normal. It has no accelerated level of data points, or it's not platykurtic, neither leptokurtic. But if it's greater than 0 as a kurtosis, then it would be leptokurtic. And again, that's where we have the opposite of the platykurtic, where we have more data points that seem to be collected around the mean, or around that central tendency, and there's a distinct peak within the data. So based off of these types of examples here of how we would evaluate this, we would say for the examples that are illustrated here, all of them have around the same central tendency, but what's very different between each one is the variation, how spread out the data points are from that central tendency. So we might say in these examples here, the red distribution might represent more of a platykurtic type of distribution, simply because it's a little bit flatter compared to the other ones, where the blue distribution might have something closer to 0 in kurtosis because it's relatively normal and doesn't have any accelerated values that are making it more peaked or flatter than usual. Compare that to the green distribution that's on here. In this one, we would call that leptokurtic. It probably has a kurtosis that's much greater than 0, and that would just mean that there's a lot less variation around the mean. So this is a way, from a practical standpoint, as a formal measurement of the shape of our distribution. A negative kurtosis, again, when it's platykurtic and more flat, like a plateaued for distribution, that means you're probably going to have a larger standard deviation that's reflecting a lot of variation that's in our process. But on the opposite side, what we might want to prefer to have is more of a positive kurtosis, something more leptokurtic, where we have a lot less variation, which tends to be a much better thing. So what we can use then is kurtosis as a way to measure our progress. If we're trying to move our distribution from platykurtic to something more leptokurtic, then the kurtosis value could be a way that you can measure that to see if we are reducing our variation. We could use other measurements similar to standard deviation and so on, but this is just one additional way we might be able to measure any changes in the variation.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
Well, I'd like you to identify at least 3 different metrics that are used by your organization and try to do the following things. First of all, for each metric, try to pull at least 15 to 20 data points for that metric. The frequency doesn't really matter, so that it could be daily, weekly, monthly, or whatever. The point is just try to grab at least 15 to 20 different data points for each of those different metrics. And then try to run the descriptive statistics that we've described in this lesson. So as an example, if you're using Minitab, then you would go into Minitab and use Stat, Basic Statistics, and Display Descriptive Statistics, and select at least the ones that we reviewed within this lesson. And then try to answer these questions for each of those metrics, and try to answer it only using the descriptive statistic answers and not necessarily using anything else that you might have normally used, like a graphical summary. So try to answer these questions like, does the metric have a right tail distribution, left tail distribution, or neither? And are there outliers significantly affecting your metric? Is your data considered to be random? Is the distribution curve relatively flat, peaked, or neither? Of the three metrics, which one has the most variation around the mean and which has the least? And of those three metrics, which one has the biggest confidence interval and which one has the smallest?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.